Yes.
I don't.
You don't? Okay. Well, it's important you do. Here's seismic data. You understand that? Scale of 1 to 10.
No, I don't know.
This is time increasing, and events take a long time to go to far offsets. That's why this guy. Okay, and you get a lot of other events because these are reflection, internal multiples.
So it's like the seismic image
Yeah.
when you have like these
Yeah.
layers.
Yeah.
Okay.
Got it?
Yes.
So what you try to do is you have the goal of people who spend their lives. Some of the people right here, Abdul's going to spend some life trying to do this right. At least he will try to do it right. Maybe there's others. I think you're a guy. He's spending his entire life trying to find a velocity model that explains this observed data. That observed data is given by a giant supervector. D1, D2, it has components D1, D2, and you take each of these vectors here and put them on top of one another and get a supervector. Okay? So that's your observed data, and this is your predicted data. How did you get the predicted data? You have to find a different solution of the wave equation. You put a source here, and you have some assumed model, we call it V. Go ahead and explode it, and you get synthetic seismograms. We're going to call it predicted data.
Of the velocity.
Because you have a velocity model.
The velocity. We suppose the velocity model.
Yeah. And if this is big, what are you going to do? Marco. If this is a big sum of squared errors, they really mismatch, what are you going to do? You're going to hire that guy with his bogus steepest descent code, and you're going to try to find an adjustment to the velocity model. In this case, V is the unknown. W is what we use for the unknown, but V is the unknown. Okay? And then you're going to try it out, see if that new velocity model decreases, and then iterate. Okay? So let's do that, see what happens. Okay? So here's our observed, here's our predict, okay? And our predicted, we guessed the velocity model. Okay? Could be a homogeneous velocity model, so you just change the background velocity model, some big homogeneous. So we can represent the trial velocity models here. The true trial model is right here, whatever this V is, because the error went down to 0. So I don't see it right there. The waveform misfit error goes down to 0. What do I mean by waveform misfit? Here's the observed data, here's the predicted data. Is this the right velocity model I chose or the wrong? Marco.
It's wrong.
It's wrong. Why?
Because
this doesn't match that.
So everything shifted.
Things are shifted. Okay. So you subtract these two, this from that, and you get a vector, or a misfit vector, and it's very wiggly.
Yeah, but these are like waveforms.
These are the misfit. This is called the misfit or the residual vector.
So it's the full waveform, and you take the misfit.
So what you'd like to do is find a model that this is 0 practically. Okay. So this is the misfit, the residual vector, and you square all the components and add them up. And you use his 5-line MATLAB code. Can you believe he's going to spend his whole life tweaking that 5-line MATLAB code? And he still won't get a perfect result. Okay, so that's the misfit associated with this model. And so the misfit's kind of low because when you sum up some of the energy there, it's kind of okay, not great. Then you try to fix it by looking at another velocity model. Notice that the sum of the squared errors in that case is much bigger than, well, not much bigger than that. Okay. And the reason is the new velocity model just shifted this guy. You know, when you increase the velocity or decrease the velocity, events come in later time, so you shift it in the wrong direction. So when you subtract that from that, this gets pretty wacko, and that corresponds to an error like that. And this error, as you plot this waveform misfit error, as you try different velocity models, just trial and error, will go up and down, up and down, up and down. So how do you fix this? One way to partly fix this is called the multi-scale method. And we call that the problem of cycloskipping. And the multi-scale method is because you have very complex data and a very complex model, it means that likely there's some really highly nonlinear relationship between data and model because of the complexity between the two. Like a 20th order polynomial, or even worse, and 1,000 dimensions. So what you want to do is simplify the data. If you simplify the data, you automatically simplify the model that can explain it. Right? You going to Italy next week? It's a simple question. Yes, he's going to go to a marriage ceremony, I think. Right? Whereas if I ask him, well, are you going to go to airport at Jeddah, and then you're going to fly to Milano, and then you're going to take a bus, there's a complex set of events that are probably, you can't get a simple answer to. You go, well, half is right, half wrong, Okay, so you want to simplify the problem. And how you simplify the problem, the input and output, is there's many ways to do it. You skeletalize the what's most important. In this case, you just pick the first arrival travel times. Give me a whole lesson in full waveform inversion. And then you have a travel time misfit function. Notice you don't have such complexities in the data, and so therefore the model that can explain this data is probably pretty simple. You don't need all the variations of the model and layers and stuff. So the misfit function is going to be pretty simple. You don't see all the wiggles here. When you try different models, then it goes down to 0. Okay. So therefore, when you do a gradient descent approach, you quickly make progress. Yeah.
Yeah. So I go back to this first plot that is in gray.
Yes.
All these lines correspond to different waveforms and to look vertically, right?
Right.
Okay.
Here I only have one parameter per trace now. It's called travel time. Here I have 1,000 parameters per trace.
Okay, so if I consider just one, I will get
Important
only one
parameter.
peak. I will get only one peak of the wave.
Yes.
Okay.
Okay. And that's very important. I mean, our intuition says time of flight information. I don't need amplitudes. I don't need lots of wiggles. Just give me how long it took the direct arrival to get from here to there. That's going to give me probably good enough information to get the velocity model. So you have this travel time misfit function. It's you skeletonize the data, so therefore you skeletonize the misfit function. It's simpler. And so another way to skeletonize the data is you low-pass filter the data. Do a low-pass filter in the data. Notice there's a lot of high-frequency wiggles here, not so many here. And I actually computed this. So notice it's going to be a smoother relationship between model and misfit function now. And that's what it is. So if you started over here, you might get stuck here, but if you start over here, you get stuck much earlier. Okay. So this multi-scale strategy of where you decrease the complexity of the input data is a very fruitful approach for FWI and other nonlinear problems. And the same thing can be true for neural networks, because what they do is they have input data, and then they kind of go through a bunch of layers, and you get a picture of the W's, say, or the outputs after you do the matrix vector multiplication and the threshold. You get a picture, you get a super vector that can be turned back into a matrix. And what they'll do is they'll skeletonize this data in the next layer by coarsening it up. Okay, so they'll take an average of these guys here, and the average, or not even the average, sometimes they'll take the maximum element value in this little 2x2 set of pixels, replace it with this maximum value. Same thing here. What's the maximum value of these 2x2 set of pixels? Lippmann. 8. What's the maximum value here? Okay, and so on. So this is a way of doing a low-pass filter on your data to help make your procedure more robust. Half of a neural network diagram. We know what this means. This is a big matrix times some input vector x given by t. And we have the motorcycle example. So let's go ahead and put the nodes where the input elements are x1, x2, x3. And the output is t1, t2. And this corresponds to the elements values of the input vector going in t1, right? This is the first equation giving you the right-hand side T1. And these element values are W11, W12, W13. But if you have two nodes here, not just one neuron, but two, then you're going to get another row vector dot product. And that's when you feed the X values into this black neuron, but you weight them by different weights. So I'm just taking what you already know, and I'm trying to make that translation to a neural network diagram, for two nodes anyway, right here. But this is only half the neural network story, right? Luckman, what's the other half?
We have to apply the function, what was
Marco, what's that function
The
called?
nonlinear activation function.
the activation function.
Ooh, it's getting fancy. I like the short function. An all or nothing function. Almost all or nothing function. So I'll just symbolize that by that and that. And so this is the whole neural network story. Okay, we're getting very close to talking specifically about neural networks. Okay. Step length, that mysterious thing called step length. I'll go through this rather quickly because it's in the book. But here's this alpha. So what you can do is you can kind of set a direction. You're moving along. And say that direction is right here. And that's our minus delta epsilon direction, going downhill. But you don't know how far to go downhill. How far you go downhill is governed by this guy. The bigger this guy is, the more you're going to go downhill. And tell me when I want to stop. Look,
There.
right here?
No,
Why don't you stop here?
come backward to the point here, somewhere here. Yes.
And why are you stopping here?
Because we can change the direction to inward again.
What?
We can change the direction to the center.
Well, I know, but why are you stopping right here?
Because it's closest to the next counter.
Because if you can imagine in your heads, what you're doing is you're going from a high elevation in the misfit function. When you go here, it's a lower elevation, right? Right?
Yes.
And if you go here, is it lower or higher than the previous point?
Lower.
And if you go right here, is it higher or lower than the previous?
Lower.
If you go right here, it's higher or lower than the
It's
previous?
getting higher now.
It's getting higher? But you stopped right there.
Yes. That's right.
When do you want to really stop? You really want to stop when you
Touch.
kiss a contour. And by kissing a contour, it means that delta epsilon is perpendicular at the old starting point. The old starting point we'll call W1. It must be perpendicular to what, Luckman? W2 at the new, hopefully your new starting point, okay? So it's tangent to the contour here. Notice when it went from here to here, it always cut across contours until it finally kissed a contour. That's when you stop. So what you can do is you can, got the wrong one. Exact lines, okay. What you can do is you can define a direction you're going to move in, and in general it's called a function f. It's like your misfit function. And you're starting at some point x, and you want to move along the delta x, that's in this case a gradient direction. And you want to find out how far you move. Well, you can expand this in a Taylor series like we've been doing now for the last half hour. And you get a gradient dotted into delta x, and then you get the Hessian with the directions specified. Is delta x variable? No, that's fixed. It's going to be a linear gradient. So that's this direction. And it has an alpha squared. You know, go through the algebra, you have an alpha squared there. Because you're moving in the alpha delta x direction, so alpha delta x transpose times h times alpha delta x, so the alphas just factor out there, you get an alpha squared there, okay? Okay, so what you do is then you want to see how far you need to go, and how far you need to go in that fixed direction says that, gee, if I were to plot this guy up, I don't know if I can do this very well. A, B, C. So I'm going to plot the value of epsilon along this red arrow here. Okay. We have A, we have B, we have C. I'm going to plot A, epsilon. You start up here, look, how does this plot look? Should I go down or up? Because I'm moving from A